Okay, let's work problem 1359 from the end of chapter questions. This problem reads the activation energy of a reaction is 56.8 kilojoules per mole, and the frequency factor is 1.5 times 10 to the 11th per second. Compute the rate constant at 25 degrees Celsius. So from experience, I realized that this question has to do with something called the Arrhenius equation, which is discussed in chapter 13 of your book. The Arrhenius equation is an equation that relates the experimentally observable rate constant K to a couple of factors. Okay, it's kind of a very useful equation for us because it allows interrelation of the rate constant with the activation energy, with the Kelvin temperature of the reaction, and also A, which is the so-called frequency factor. So before we start the mathematical work on this problem, I wanted to take a second to sort of talk about these different variables and really what they are. Okay, so the first one is A. It's called the frequency factor. Sometimes it's referred to as the pre-exponential term, whereas this e raised to this business is the exponential term. So sometimes this is called the pre-exponential term. You'll hear that thrown around. Also the frequency factor. Well, frequency factor is going to be given to us in this problem. So it's going to have this value of 1.5 times 10 to the minus 11th. I could even write that in here to get ahead of myself, all right? Units of per second on that, okay? And what that number tells us is the rate of molecules approaching this transition state per second, okay? Now, to understand what we mean by that, think back to our reaction coordinate diagram, where we have our reactants and our products at the final condition, and in between there's this hump, okay? That hump corresponds to the activation energy. So basically what we're measuring here with this frequency factor is the rate at which molecules for a particular reaction can approach that activation energy or that activated complex or that transition state. The rate of approach to the transition state might be a better way to say it, okay? So in this particular case, that's reasonably fast. There's 10 to the 11th approaches every second, okay? It's reaction dependent because some reactions are very complicated in terms of what bonds need to break and reform to make products. So this number is definitely going to depend upon the complexity of the reaction. And every reaction is a little bit different. So every reaction has its own frequency factor, A, okay? Now, I know I need to take the A and multiply it by the second term. Okay, that's the dot for multiplication. That second term is called the exponential term. The exponential term, for hopefully pretty obvious reasons, right? Because we're taking something and raising it to an exponent. In this case, we're taking e and raising it to an exponent. Now, e is the base for natural logarithms, and it's got a value of 2.71828. So we're going to take that e and raise it to an exponent. I'm going to erase this. Unfortunately, it's just kind of in the way. Hopefully you're able to read through that. Just defines what the exponential term is. Well, we haven't talked about that explicitly, so I'm going to return that in a second. But I had to take E, this number, and raise it to the negative EA over RT. Now, EA is the activation energy for the reaction. R is a constant. It has the value of 8.314. T is the Kelvin temperature. Okay? All of that is in this exponent. Now, in this particular case, I'm going to start with Kelvin temperature. It's 298. Now, how in the world did I know it was 298? Well, I was told in the problem I'm operating at 25 degrees, right? It's consistent with 298. Now, also in that denominator, I need to multiply that Kelvin temperature times R. R has the value of 8.314. The units attached to that are joules per mole per Kelvin. Joules per mole per Kelvin. Okay, so the Kelvin works out because I have Kelvin here, so that's going to cancel. But then I have joules per mole per Kelvin for this unit. All right, so EA must be in joules units. Okay, now usually activation energies are pretty large, so they're stated in kilojoules per mole. So you have to convert 2 joules. It's a very, very typical step. But you got to make the units draft. So I'm just going to do that here kind of on the fly, because I know that this is in joules per mole for Kelvin. My R is in joules per mole for Kelvin. So I need to make this in joules as well. All right, so I've got my mathematical terms. Now, what is the importance of this exponential term? We haven't discussed that yet, and unfortunately I kind of erased what was said here, and you can page back and look at that if you want, okay? But the significance of the exponential term is this is a number between 0 and 1 that basically describes what fraction of the molecules which approach the transition state have sufficient energy to overcome the barrier to form products. Because remember, if you can't overcome this energy barrier, the energy of activation barrier, you're not going to form products, okay? So the frequency factor A tells us the rate at which our molecules can approach that transition state. The exponential term that we multiply the frequency factor by tells us the fraction of molecules with sufficient energy to overcome the activation energy barrier. So if you multiply them together, this is the fraction of approaches which overcome the barrier. This is the rate of approaches. It makes sense. Then we get K, our kinetic rate constant. This tells us essentially the rate at which we can form our products because it combines both of these terms, right? Mathematically, it's defined in this way through this Arrhenius equation. We've already plugged in our variables. And I think we can see we're basically ready to solve this equation. We take E, the base for natural logarithms, and raise it to the negative EA over RT, where R is like that constant again. This is our Kelvin temperature, all right? And then we multiply it by our frequency factor. Now, if I do that on my calculator, it yields a value of 16.58 per second. This is what I get just right off my calculator. If I'm going to sort of truncate that to 2 sig figs, I suppose, I'm going to round up to 17 with units on K of per second. Okay, so this basically tells us the rate constant 17 per second. And when you combine these two considerations, that is the energy consideration, what fraction of molecules has sufficient energy to overcome the activation energy barrier, and just what frequency do these molecules approach the activation energy barrier. Okay, so that's the Arrhenius equation problem. I hope it was useful for you. It shows its usage. Again, we're going to use this equation all the time to basically interrelate variables such as frequency factor, activation energy, and temperature. Those are really your big three. In some problems, maybe you're given the rate constant at a particular temperature, you're told the activation energy, and you're asked to find the frequency factor. You could rearrange variables and do that. In other cases, maybe you're asked, what temperature do you need to heat things up to achieve a certain rate constant, okay? But as long as you focus on this equation and are able to sort of functionally use it algebraically, you can basically find any one of those three variables if you're given the other ones, okay? So this is the Arrhenius equation. It's useful for discussing temperature dependence, right? Know these factors and sort of what they correlate to or control. I think that that's an important aspect of understanding this Arrhenius equation. It's also kind of fun and cool, sort of from a physical perspective, right? You can understand this is the frequency of approaches, and this is the fraction of approaches with sufficient energy. So that's the Arrhenius equation.